Hey everyone, and welcome to This Explainer. Today, we're diving into something that honestly sounds straight out of a sci-fi movie, but it could literally save human history. Just imagine taking everything you know, every single piece of data, and encoding it into a virtually indestructible piece of glass that lasts for millennia. Sounds totally incredible, right? Well, the crazy thing is, it's actually happening. So to really wrap our heads around why this is such a big deal, we got to talk about the sheer scale of our data problem. Every single day, think about that, every day, modern civilization pumps out a massive 2.5 quintillion bytes of data. We are generating information at a pace that is just completely unprecedented in human history. We're talking everything from vital medical records and scientific research, all the way down to our personal memories and our global cultural heritage. But here is the crazy part. We're trusting all of that, our entire digital legacy, to incredibly fragile hardware. I mean, your standard hard drive. It usually kicks the bucket in just 3 to 5 years. Even magnetic tapes, which are the industry standard for archives, only survive 5 to 7 years under perfect conditions. This forces companies into this endless, wildly expensive cycle of copying data to new drives before the old ones die. And that is exactly why Microsoft's Project Silica is trying to redesign storage from the ground up, to lock data into glass for at least 10,000 years. Here's our roadmap for today. We'll start with the digital preservation crisis, then look at enter Project Silica. From there, writing data with lasers, the borosilicate glass breakthrough, the zero-power archive, and wrap up with the road to commercialization. All right, part 1, the digital preservation crisis, or as some experts are terrified to call it, the looming digital dark age. To keep all this fragile data alive, we're stuck in this constant loop of migrating it to new servers. And wow, is that an expensive headache? But it's not just an IT problem, it's actually a massive environmental burden. Get this, data centers already gobble up roughly 1% of the entire planet's electricity. A huge chunk of that energy, not to mention the intense cooling required, goes straight toward maintaining and migrating archive data that people might rarely, if ever, actually look at. We are literally burning massive amounts of energy just to keep our history from rotting away. Which leads us to part 2. Enter Project Silica, and how storage is being totally reimagined. This is where Microsoft comes in, and their progress has been lightning fast. You might actually remember back in 2019, they made headlines by storing the original 1978 Superman movie, which was about 75 gigabytes on a piece of fused silica glass. Well, since that proof of concept, they have managed a 100-fold increase in density. Today, they are cramming 7 terabytes of data onto a little square glass platter roughly the size of a drink coaster. That volumetric data density is actually higher than current magnetic tapes. And that insane durability is exactly why places like the Global Music Vault up in Svalbard, Norway, are teaming up with Microsoft. They want a foolproof way to protect humanity's musical heritage from, well, environmental catastrophes. Because this glass is basically indestructible. It laughs at electromagnetic pulses, boiling water, microwave radiation, even severe scratching. Plus, it uses what's called a worm architecture, which stands for write once, read many. So once the data is laser etched in there, it simply cannot be altered. You get a completely tamper-proof archive. Okay, moving on to part 3, writing data with lasers and how we achieve light-speed precision. So how do they actually do it? The secret sauce is something called a femtosecond laser. This thing fires ultra-short optical pulses that last, get ready for this, mere quadrillionths of a second. When these insanely fast pulses hit the glass, they create permanent, microscopic structural changes deep inside the material itself. Researchers call these tiny, multidimensional pixels voxels. So it's not just scratching the surface, they are encoding data in full 3D across multiple layers right inside the glass. The whole operation breaks down into 3 really specialized steps. First up, those femtosecond lasers zap the voxels right into the glass. Then, to read it back, they use a computer-controlled polarization microscope that scans the glass to read those analog optical patterns. Finally, and this is where it feels very 21st century, Microsoft uses machine learning and their Azure AI infrastructure to flawlessly translate those optical patterns back into a perfect digital file. Now, here's the catch, and it's a pretty big one. Project Silica is absolutely not going to replace the SSD in your laptop. It is explicitly built to be an ultra-cold deep archive. While it reads data at an okay 30 to 60 megabytes per second, getting a massive file retrieved from their robotic library comes with a service level objective of 15 hours to last byte. Basically, getting your data back takes hours, not milliseconds. It's designed for stuff you absolutely cannot lose, but rarely need to access in a hurry.
All right, part 4, the borosilicate glass breakthrough. Let's talk about the big shift. Up until February 2026, this technology relied on fused silica glass, which is super expensive and pretty hard to get. But the massive breakthrough? They figured out how to shift over to borosilicate glass. As Microsoft research pointed out, this is the exact same cheap, highly available stuff your oven door and everyday glass baking dishes are made out of.
And honestly, switching to this everyday material was a total game changer. It obviously slashes manufacturing costs, but the engineers didn't stop there. By using a new technique they call phase voxels, they now only need a single laser pulse to create a data point. They call it pseudo-single pulse writing. Even better, they developed a multi-beam delivery system, meaning they can write multiple data points at the exact same time, which completely supercharges those traditionally slow write times. Oh, and the new microscope reader, it only needs one camera now, down from 3 or 4, which shrinks the hardware and makes the whole setup way more efficient. This brings us to part 5, the zero-power archive and its passive infrastructure. So, we've got cheap glass, lightning-fast lasers, and crazy dense data. But where do you actually put these glass plates? Well, they don't go in a noisy, power-hungry data center. They sit in what's called a passive library. Once your data is baked into that glass, it takes exactly 0 electricity to keep it safe. No AC cooling, no background integrity checks, nothing. When you finally do need a file, little autonomous battery-powered robotic shuttles, part of a system called Rascal, zip along rails to grab your specific plate. And because writing and reading happen in completely different physical machines, you get this amazing air-gap-by-design security. It is physically impossible for ransomware to mess with your files once they are in the glass. Finally, part 6, the road to commercialization. Let's look at the actual market reality.
As amazing as this all is, we have to look at the business side. Microsoft isn't the only kid on the block here. There is a German startup named Cerabyte, backed heavily by the traditional storage industry, and they're going after a totally different market. See, while Microsoft is building this deep archive for Azure where access takes hours, Cerabyte is pushing for an active archive using ceramic glass. Their goal? Access times under 10 seconds by 2030. It's a fascinating technology race, with these brilliant companies trying to solve entirely different pieces of the massive archive puzzle.
We also need to keep in mind that you can't just go out and buy a Project Silica drive today. Microsoft has been pretty upfront, admitting they are still 3 to 4 development stages away from launching this commercially. Even with that huge borosilicate breakthrough, they still have to figure out how to scale up manufacturing, and they really need to drive down the massive upfront costs of those precision robotic facilities and those fancy femtosecond lasers. But here is the bottom line. Century-scale, even millennial-scale data preservation, it is officially crossing over from science fiction into actual hard engineering reality. It's really happening. And that leaves us with a pretty profound question to wrap up on today. As this technology gets ready to permanently preserve human history, completely immune to time, water, and power outages, what part of your own history would you choose to immortalize? Thanks so much for hanging out with me on this explainer, and I'll catch you in the next one.